So good afternoon, everybody. I'm Nick Nystrom. I'm Interim Director of Pittsburgh Supercomputing Center, following the footsteps of Mike Levine and Ralph Roskis, who many of you know, who retired this summer. And of course, Jim Kasdorf, who used to be at these meetings, also one of the founders. With me, co-presenting, is Paola Buitrago. Paola is relatively new to PSC. She's leading artificial intelligence and big data with us. Prior to that, she was at PSC she was at a university where she developed courses in machine learning and the curriculum and taught there for several years. Then went to Fermilab, did some work in scientific workflows for neutrino physics. Then went to Carnegie Mellon, focused on deep learning, especially generative adversarial networks that have a lot of potential for dealing with the problem of limited data that we've heard about a couple times during this meeting. And now is at PSC, where her entrepreneurial background is really feeding into the industrial partnerships, again, that we've been hearing today. And as for myself, my own background is physics, chemistry, and math, like many of the people on the panel. Done a lot of work in HPC architecture, software engineering. Right now, my own work is mostly focused on the intersection of public health and life sciences and machine learning. So we're here to talk today about AI advances and breakthroughs at PSC. First, for those that don't know us, PSC is a national supercomputing center. We've been around for over 30 years, since 1986, really focusing on leadership class computing, a lot of large parallel systems, a lot of innovative systems. We have 19 supercomputers, 19 of which have been either the first in the world, 9 of which have been either the first in the world or the only one of their kind. We'll talk a little bit more about where that is and where it relates to AI in a moment. We have a lot of research going on internally, and our support is from national agencies, NSF, NIH, DOE, and so on. Also Pennsylvania foundations and industry. Right now we're operating 2 unique systems. One is Bridges. That's been mentioned in a couple of talks here from Ed this morning and from others. Bridges really combines HPC, AI, and big data. And Anton 2 is a purpose-built system for molecular dynamics, and many of you know from its presentations at the SC conferences. Both are unique in the world. They're allocated by Exceed and by the national academies, respectively. The leadership transition I mentioned, we're moving toward a permanent director now. At PSC, we also have new areas of focus. One is a new group in AI and big data. We've been doing work in those fields for years, but we didn't have a focused group doing nothing but that. We now have that with Paola leading it. And we're also broadening what used to be biomedical applications to computational biology, which now also includes a public health applications group under it. And we're doing a lot to strengthen our ties with industry. As I mentioned, Bridges is a unique system. It's a $17.2 million NSF acquisition. It really merges different compute elements: large memory, 12 terabytes of RAM, 3 terabytes, 120 gigabytes. It has a number of GPUs in here. They're really good for deep learning, as you'd expect, and on which we are running the normal frameworks that Paola will talk about more, so I'm going to go fast on that. It was the first deployment in the world of OmniPath, and that's pretty significant. So why did we build Bridges like we did? First, it was because it's what users wanted. This was totally user-driven. We announced this at SC 2015, and at that time, people were starting to talk about how do we put together HPC and AI. And it was interesting to say, we're already doing this. The system will be on the floor within a couple of months. We deployed in January, as soon as OmniPath was ready. And it really does do that. So we're tightly coupling these different kinds of computing to deliver on the big data as a service, AI as a service, and HPC as a service. And really, the key to that is the software environment. It's being able to provide the tools that people are using: Python, R, MATLAB, the deep learning frameworks, prioritizing interactivity so people can actually work and do analytics. They can do development. They can work on their networks. And then standing up persistent database and web servers so people can have things running all the time. Those will let us do a lot of these things as gateways. And the gateways, it's a NSF word for a nice user portal that lets people really democratize access to these services. They don't have to learn the Linux command lines. They don't have to log in. They can just work from a web browser. And we're running various containers, especially Singularity, also some Docker. The architecture looks kind of like this. And the point here, you've all seen this diagram, I think, at different places. But the point is I've highlighted the different components that are really ideal for AI and deep learning and how they work together. And so what we have here is the GPUs in green, obviously, OmniPath connecting them, being able to do training across multiple nodes with multiple GPUs at high bandwidth through OmniPath. And then interfacing to the storage in white, other kinds of compute nodes that may be doing inferencing on Xeons, for example, and the large memory nodes that could do some large memory, Java, Python, other pieces of machine learning stack that complement what we do in deep learning. We work with a colleague who likes to characterize as you have deep learning, but you also have all of the other, what he calls shallow learning around that, the clustering, the classification, the other things that also have to happen. I put up one slide on GPU nodes just for people who are not yet using the P100s. We got these in October. They were among the first ships of P100s. The last point I personally want to make is the allocations on bridges are nationwide. We have over 300 institutions using it, over 1,000 projects, close to 3,700 users, and 101 fields of science. So it's very widely used. It's from people across the country. I just pulled out 4 projects here that are from Pacific Northwest National Lab, a DOE lab. This is really computational chemistry, so not the standard images and text. Over here in Penn State is genomics. So my own research is also in deep learning on genomics. And so there's a whole breadth of things here. They're not just images, video, and speech. And we'll get more into that. So we're running slow, so I'll hand over to Paola right now.
Thank you, Nick. Thank you, everybody. It's a pleasure being here. Nick has shared with us 4 of the projects that are artificial intelligence-based and random bridges. We have plenty more. And I want to share one of the most recent success stories in the artificial intelligence realm. This is a collaboration between Professor Thomas Sandholm at CMU and PSC. And this is a story that was documented by our partners at HP, and hopefully the video plays well.
This is a building where a machine room is.
I'm not that good a poker player, and I didn't really play poker before we started to do this, but I've been watching this artificial intelligence for 14 years, so I learned a thing or two. I know some things that some of the pros don't. So I'm Thomas Sandholm. I'm a professor here at Carnegie Mellon University. I've been working on artificial intelligence since 1989. Poker is a great benchmark because it is a huge game. It has 10 to the power of 161 different situations. That's more than the number of atoms in the universe, and even if you had for every atom in the universe a whole other universe and calculated those atoms, it would still be more than that too. So really, to do serious research in the area, you do need to use a supercomputer.
I'm Nick Nystrom. I'm the Director of Research at the Pittsburgh Supercomputing Center. One of our recent initiatives with Professor Thomas Sandholm is to really set a system where he can test and demonstrate an artificial intelligence he's been developing for competing against the world's top human poker players. And we designed a custom topology just to make this kind of AI possible. The reason that we chose Hewlett-Packard Enterprise was really their depth. We were trying to build a system that would let people do things they've never done before, and those problems require very large shared memory. In Bridges, we have HP Integrity Superdome X servers with 12 terabytes of random access memory each. We also have 800 Apollo 2000 servers and HPE DL580 3 terabyte servers. And so bringing all those different components together was essential to Bridges.
The algorithms that run on the supercomputer come up with their own strategy for playing the game. They don't take any data as original input. They just compute from the rules of the game and figure out their own strategies. In January, we ran this Brains versus AI competition where we brought in 4 of the top 10 heads-up no-limit Texas Hold'em professional players.
Initially, the players were doing quite well.
We're like, we figured this out. It has these holes. We're going to take it on. And then it improved.
In a few days, Libratus had learned what they were doing. It closed those holes.
It limps, it min raises, it raises to 2.5. Most people, when they play, they only raise.
some people like limp and raise to do this much pre-flop variation. It's not something that any human would be able to do.
As the players found more holes, Libratus identified those.
Just in Libratus fashion, he hits 2 pair on the river.
We beat them by 14.7 big blinds per 100. That was the first time AI had been able to beat top human players.
And that's really exciting because the test of artificial intelligence is when can it surpass humans?
In theory, there is a way to beat it, but we just don't know how.
It's quite a really interesting use case. As I was saying, I want to mention that this particular problem was not addressed with deep learning. This was done with the other type of machine learning. As I mentioned before, the video finally play the real world examples or problems where these kind of apply are like extremely ample negotiation, strategic pricing. But the computing and the storage that was required to make this happen was huge. Only in bridges, it was 19 million core hours. And what Libratus does is that it creates a knowledge base based on what it has seen, the rules that it knows from the rules of the game. And up to the moment when we have this demonstration on January, it was 2.6 petabytes of knowledge base. There has been other 2 demonstrations, one in China, where Libratus was denominated the Cold Poker Master. And it played against 6 strong Chinese poker players that, as expected, were defeated by Libratus. It was also demonstrated at IJCA in Australia recently as well. So this success story is just one of the many we have. But this is like the most significant because this is literally writing history based on the experience we have and like seeing how successful it is converging HPC and AI and like the experience we have collected over the past 2 years. We decided to launch this group focused on artificial intelligence and big data. And what we want to do is like articulate all the services and all the expertise that PSC can offer, also partner with UPIT and CMU and make sure or aim at providing big data and artificial intelligence as a service and make whatever we can to make it easy for users and researchers to access the relevant data resources, data repositories specific to the particular field. Oh no, we have 2 minutes left. And well, I'm going to try to go fast. And we also want to lead the acquisition of technologies oriented on AI and big data. We want to offer access to businesses that are starting, that are new to artificial intelligence. We want to help them during that process. And of course, education and training, communicating results. I'm going to go fast. Our focus is from the project lifecycle that you would expect in data science. So not only the training, because we have been focusing, that's an important and painful part of an artificial intelligence project. But we also want to focus on the time to science, and for that we need to understand also the other, or like offer tools and the expertise for the other parts of the life cycle. I just want to mention in our experience, like what we do is really user-driven. These are the deep learning frameworks that we support. As users come and request a new framework, we offer the support for them in the machine. This is just one of our team members, Joe Welling, who has been in charge of this task. Particularly on training, we lead the Exceed HPC training on big data. So we have offered a total of 8 big data workshops. It's big data and deep learning. We have reached around 2,400 registered participants. And I'm going to go to the next one. These are like the institutions that we are reaching with our training. We are making sure like we offer it remotely, and we just want everyone to be able to access this information. So the next workshop we have is next week, Tuesday and Wednesday. You guys are all welcome. invited to join us. It's going to be 2 days of big data. Big data and deep learning. First day is going to be big data, Hadoop, and Spark. Then we are going to have deep learning on TensorFlow. Hands-on projects is going to be real-time interaction with the lecturer and also support. And if you cannot make it to the site and you have special needs, we can also accommodate that. So there's no excuse to miss it. From the beginning of Bridges, we have also been offered the system for the support of courses, university courses that involve the artificial intelligence and big data. These are some of the ones we have supported. So like the students doing their projects and final course projects or mid projects during the classes. We have that. Like the last one we did was, well, that was quite interesting, was deep reinforcement learning at CMU with Professor Roslan Salakutidinov, I think, and Katerina. And here we had 200 students. So it was quite an interesting challenge. And from that we learned, like we made sure we get back to professors and students and learn what went well and what didn't, all in order to offer a good user experience in the future. I'm gonna go back to Nick, if we still have a couple minutes.
I'll just wrap up real quick. Yeah, thanks, Paula. Yeah, and so that was quick. We are making, Earl has the slides, so they'll be available online. Just as two other real quick things I want to touch on. One is a workshop. We ran this workshop with CMU and Johns Hopkins this summer. It was an 8-week long. It was really a 2-week course plus a 6-week hackathon with people looking deep into language and speech and machine translation. Brought together 60 researchers from around the world to really do science in this machine. And what we find here is it's like the courses Paula said. These are huge courses. I don't remember graduate students with a graduate course with 200 students. But when they're coming and beating on bridges and actually getting to get work done, that's what you can do with AI at scale, to train people, to let people train models and do research and scale out. This is another example, 60 world-class researchers. Their final presentations are down here at this link, so you can get their slides, their presentations. Most of them are open. Real quick look at the breadth of projects using bridges. There's a lot going on here. There's fundamental CS research on improving deep learning algorithms. And that's going to push the field forward. There are all the things you expect in images and text. There are people looking at a lot of things in bio. This is an interesting one, the automatic evaluation of scientific writing. This is improving the quality of journal publications for people who may not be native English writers. There's just a lot going on here. There are people developing software systems. There are people applying it to science. And in many cases, we're working, as Paula said, we're reaching out to industry. We're looking at ways to help businesses get going. We're going to be launching something new on that line very soon. If anyone's interested in that, whether it's a startup or an established business wanting to do more with big data and deep learning, just get in touch with us. The very last thing I just want to highlight is one more success at PSC. This is actually ongoing. And this is looking at connectomics, understanding how our brain is wired from scanning electron microscope images, and working toward being able to do segmentation from these things into building neurons so we can understand the human brain. This was easy. This is a zebrafish. It's about a millimeter long. Our brain, if we did the whole day, would be about 1.4 exabytes in size. And so automated means are needed to do this sort of thing, to do the reconstructions. This will lead into research on Alzheimer's, on Parkinson's, on all sorts of neuro diseases. And so it's really vital research. This is being done actually by a couple of interns at PSC under Paula's guidance, and prior to that, some other folks at PSC. So I'll leave it there since we're over. The slides will be available. We'd be happy to take any questions.